Here's a wild one. The Earth's rotation,
Oh, yeah.
you know, where we set our clocks by, it isn't all that consistent.
No, it's not. It kind of rolls around. And on June 29th, the Earth was 1.5 milliseconds, I should say, short of 24 hours. We all kind of assumes it takes exactly 24 hours for the Earth to complete one rotation, but it actually speeds up and slows down continuously. It's rarely ever exactly 24 hours. How cool is that?
That is actually really cool. And that being said, overall, scientists believe the Earth's rotation is slowing down over time, and climate change actually might be the reason. So we want to bring in Dr. Paul Sutter, who's an astrophysicist at Stony Brook University and the Flatiron Institute. We love having you on, Dr. Sutter. Let's get right into it. How is it possible that we just saw our fastest day on June 29th, but overall we're seeing the Earth apparently be slower? How does that all figure out?
Yeah, it turns out that the universe is kind of messy, which is great because it means job security for people like me. And there can be long-term trends where the Earth is generally slowing down over centuries or millennia, but then there are also these tiny little blips, like what we're seeing recently over the past few years, where the Earth has been speeding up just a tiny, tiny bit.
I love that you said it turns out, by the way. I don't know if anyone else picked up on that.
A little pun. Just a little.
Yeah.
But you know what? What are some of the reasons for these slight changes in rotation speed?
Well, the overall reason is we have no idea because the Earth is so complex. But there are some options. If you've ever seen a figure skater or a fidget spinner, if you change just a little bit about how that figure skater has their arm positions or the arrangement of stuff on the fidget spinner, it will change the rotation speed. So maybe the core or the mantle of the Earth is contracting a little bit, or our oceans or atmosphere are getting a little warmer and extending out a little bit, or even circulation patterns in ocean currents or atmospheric currents are rubbing up against mountains or pushing mountains. All of that can play a role at the level of detail and precision that we're talking about.
Do we know, is this something we're now just figuring out, or are we able to somehow look at tree rings? I'm just saying, it's not really look at tree rings to see how fast or slow the Earth has been going way back in time.
So going way, way back in time, we are talking billions of years. We know that our days used to be a lot faster, something like 6 hours faster than they currently are. With the current measurements that we're capable of, like we're talking millisecond accuracy, and that we only have records going back a few years.
Wait, why was it faster, and how do we know that?
Oh, we know that for a few reasons. One of the biggest reasons we know is that the moon used to be a lot closer to the Earth. And as the moon orbits around the Earth, the moon gently spirals away from the Earth, and that causes the rotation of the Earth to slow down. So the dinosaurs knew a slightly longer day.
Interesting.
It is remarkable how nonlinear this problem is how all these different factors intertwined with one another complicate it. So once you have 2 factors, you can get it, but 3 and then beyond, it's almost impossible to tell what's causing what. I love that. You know, we have seen some theories about glacial ice melt and how that would impact the rotation. Now, how likely is that theory to be true?
Absolutely. Anything that affects how mass is distributed on the surface of the Earth, if you have a lot of stuff at the poles versus a lot of stuff at the equator, that is going to change the momentum of the Earth as it spins, which will change the length of the day.
All right, what's the Chandler wobble? I'm assuming it has nothing to do with the show Friends. That's the first thing I thought of.
Yeah, so one of the things that can cause a change in the length of our day is where our magnetic field currently points. So the magnetic north does not line up with geographic north. And the magnetic north is moving around, and we call this motion Chandler wobble, named after the scientist who first observed it. And this might be connected to the current speeding up that we observe in the length of the day.
So some of this could be terrifying if you look at it in sort of the wrong way, because someday we know that the sun is going to engulf the Earth in billions of years from now. But do we need to worry about any of this stuff, all these slight changes and these wobbles?
Please say no. I have enough to worry about.
The answer is no, thankfully. We're talking about millisecond differences. And over the course of an entire day, that's like 1 in 100 millionth change in the length of the day.
All right, so are we going to continue to slow down as the moon continues to pull away, as you were talking about in the
Yeah, like
future?
500 million years from now, we will have a longer day, but not today.
All right, so are we going to have to add any leap seconds or years to our calendar with all this being said?
If this trend of the Earth slightly speeding up by a few milliseconds every day, if you add that up over a few days, a few months, a few years, maybe even a few decades, if this trend continues, we may actually need to do a negative leap second, an anti-leap second to account for that.
That doesn't get confusing or anything at all.
Not at all.
Yeah.
Dr. Paul Sutter, you
Yeah.
always take complicated, subjects and make them understandable. So we appreciate it. Astrophysicist at Stony Brook University and the Flatiron Institute.